Good afternoon, everyone. My name is Junda Zheng, and today I'm going to present our work on a new technique for testing SMT solvers, titled Bounded-Exhaustive Subspace Diversification for SMT solver testing. This is a joint work with my mentor Peisen from Zhejiang University. And today we'll start by discussing why testing SMT solvers is so critical and identify a key gap in current testing methodologies. Then, I'll introduce our novel approach, which we call subspace diversification. After that, we'll dive into the evaluation of our tool, Canary, looking at its effectiveness in finding bugs and enhancing existing tools. Finally, I will conclude and open the floor for questions. SMT solvers are core reasoning engines. They power many advanced software engineering and security tools. This includes symbolic execution, program verification, and synthesis. In fact, their application is incredibly broad, also covering program repair, refinement, and even critical industrial use cases, like verifying the access control policies of Amazon Web Services and ensuring the safety of radiotherapy machines. These tools are the backbone of modern program analysis. The ecosystem's reliability depends on the SMT solver's correctness. But there is a problem. SMT solvers have bugs. These bugs are not minor. We see critical soundness bugs. A solver might give a wrong set or unset result. We find invalid model bugs. The provided solution does not satisfy the formula. There are also crashes and hangs. This stops the analysis. A single solver bug can invalidate results. This is particularly dangerous because the systems that rely on these tools are often safety critical. A single incorrect verification result could lead to serious security vulnerabilities or system failures going unnoticed. This threatens our trust in verification systems. So, how do we test solvers? There are two main approaches. Generative methods create new formulas. They can produce many tests, but it is hard to target complex solver features. Bugs often hide in these corner cases. And mutational approaches modify existing seed formulas. This method is powerful, but the changes are often small and syntactic, like flipping an operator or changing a constant. While these methods can explore syntactic diversity, they often fail to guarantee semantic diversity. This means many of the new formulas they generate can be logically very similar, causing the solver to repeatedly explore the same narrow search area. This is a critical gap. There is no systematic semantic probing. Existing methods do not explore different logical regions of the solution space. This is where the deepest bugs are often found. So let me show you a motivating example. It triggered a real bug in CVC4. Consider this simple formula. It contains a disjunction big A or D. The formula is satisfiable if big A is true or D is true. We ask the solver to assume D is true. It returns satisfiable instantly. This explores one part of the solution space. It's the subspace where D holds. Next, we explore the other subspace. Here, the complex term big A holds. The solver suddenly times out the two subspaces, S big A and SE, are logically distinct, but they trigger very different solver behaviors. This exposed a performance bug in the solver's branching logic. This example clearly shows that the solver's behavior is highly sensitive to the region of the solution space it explores. Many solvers employ deterministic search strategies, which means for a given formula, they may repeatedly follow the same path, ignoring other regions where bugs might exist. This leads to our key insight. We must force solvers to explore different semantic subspaces. This is a powerful way to find hidden bugs. And that is the core idea of our work, which we call subspace diversification. Instead of just mutating a formula syntax, we systematically partition its solution space to guide the solver down different and often less traveled logical paths. Our goal is to force the solver to explore these under-tested regions where bugs may be hiding. We developed 3 strategies to create these partitions. They are very general and lightweight. First, we use numerical domains for formulas with numbers. We add constraints on variable ranges. This partitions the solution space. For example, take a formula phi xy. We can add the constraint x greater than 100. This is effective for finding arithmetic bugs, overflows, and rounding errors. By doing this, we can precisely test the solver's behavior when handling boundary values, large numbers, or specific numeric relationships. Second, we use Boolean cubes. This is inspired by cube and conquer SAT solving. A cube is a conjunction of literals. For a formula phi PQR, we can assert like P and not Q. This forces the solver down a specific path, and it is a general strategy that it works for all logical theories, because it operates on the level of atomic formulas. It can be applied to theories like strings or arrays just as easily as to propositional logic. Third, we use quantifiers. Quantifiers are very complex. They are a common source of bugs. Our strategy injects or modifies quantifiers. For example, a formula phi xy can become for all z phi xz. This tests the solver's quantifier logic, and this part of the solver is really difficult to get right, with common issues in areas like instantiation strategies or handling quantifier alternations. This makes it a very fruitful area for bug hunting. It also tests its decision procedures. And we implement these strategies in a tool called Canary. Its workflow is based on differential testing. And Canary takes a seed formula and applies one of our partitioning strategies to generate a new constraint subformula, and then runs it on multiple SMT solvers, in our case, Z3 and CVC5. If the solvers disagree on the result, or if one of them crashes, we flag it as a potential bug. Now, let's look at how well this works in practice. We designed our evaluation to answer 3 key research questions. First, how effective is Canary at finding new, previously unknown bugs? Second, can our method improve the code coverage of existing state-of-the-art fuzzes? And finally, does that improved coverage actually translate into finding more bugs? We tested against the latest version of Z3 and CVC5 and compared our approach against 2 leading fuzzers, fuzz and yin-yang. First, is Canary effective? The answer is yes. Over 9 months, Canary found 123 unique bugs. Developers confirmed 108 of them, and 107 have already been fixed. These are not minor crashes. They are critical correctness issues. Over 35% of confirmed bugs were soundness errors and invalid models. These bugs can silently corrupt verification results. To give you an idea of the effort required to fix this, we looked at the code commits. In total, developers modified 196 files and over 5,600 lines of code to address the bugs we found, showing these were non-trivial issues. Furthermore, our approach demonstrates great generality. This chart shows the distribution of bugs across different SMT lib logics. Canary found bugs in a wide variety of theories, from arrays and bit vectors to nonlinear arithmetic. The fact that we found so many bugs in mature and widely used theories like bit vectors shows that even well-tested components still have hidden flaws that our semantic approach can uncover. Next, can our method improve code coverage? We integrated Canary strategies with baseline fuzzers. We use fuzz and yin-yang. We then measured the results. The table shows a clear trend. Integrating Canary improves line, function, and branch coverage. This is true for both Z3 and CVC5. For example, when combining with fuzz on Z3, we saw an increase of 0.7 percentage points in line coverage. While small percentages might not seem dramatic, given the massive size of these solvers, this represents a meaningful number of previously untested lines and branches of code. This is strong evidence for subspace diversification. It forces the solver into new execution paths, and existing techniques did not reach this path. But does more coverage mean more bugs? We ran a 1-week head-to-head competition to find out that. The results in this table are very encouraging. We combined Canary with fuzz and yin-yang. The combined tool finds more bugs than the baseline fuzzer alone. We see more critical soundness bugs. We also see more crashes. For instance, when paired with fuzz, Canary helped find twice as many soundness bugs in Z3. And when paired with yin-yang, it uncovered an invalid model bug that yin-yang missed entirely on its own. This shows that subspace diversification is a powerful complementary approach. It is not a replacement for existing methods, and it improves code coverage. The better coverage boosts the bug-finding capability of other techniques. So to conclude, the core problem is that SMT solvers have critical bugs. Existing testers do not explore the semantic solution space well, and this is where bugs often hide. Our main contribution is subspace diversification, and this is a new testing methodology. It partitions a formula solution space and it guides solvers into under-tested regions. And our results are clear. Our tool Canary found 108 confirmed bugs. These were in the leading solvers Z3 and CVC5. Canary also enhances other state-of-the-art fuzzers. For the future work, we are exploring adaptive learning. This will help select the best partitioning strategies automatically. This will make the process more efficient. We also believe these principles can be applied beyond just solver testing. For instance, in developing new benchmarks or informing strategies for parallel and distributed solve. So thank you for your attention, and I will be happy to answer any questions you may have. Thank you.
Hello. Okay, good. Okay, this is a very impressive work. I found lots of bugs, but I have to ask the first question: how the author is going to take questions? Are they online with us now?
Yes, they are. Can you give me a second?
Okay. Okay. In case there's any questions from the audience, yes, go ahead. Use the microphone. Yes.
Hi, Bowen from HKUST. So currently, Canary use differential testing as an oracle. Yes.
Okay, wait a minute.
Hello, can you hear us? Oh. Hello, can you hear us? Yeah, no, they messed up something. Hello?
Oh, I can hear.
Oh, perfect.
So hello, Junda. If you can hear us, we are taking the first question. Okay, go ahead.
Interesting talk. And so my question is that currently your work uses differential testing as an oracle, but there is still a possibility that when two solvers return set, but there is still bugs. For example, the model could be different or yeah. And so any ideas on how to further review such kind of bugs? Yeah.
Well, for such kind of bug, well, we can, for example, for the invalid model, we can have test the model that is unsatisfied, and for other like corner cases for two solvers, they are both wrong. I think this case is not very frequently appears. So, and I think um, I think those bugs could be some minor, and um, so there are also some other approaches to find these bugs, but for now we found many bugs with the differential testing. So I think we could improve the approach in the future. So, yeah, so thank you.
Thank you so much for the answer.